Okay. So these are the slides. This is the memory layout. Your code. This is obvious you talk about. 400 is where your program code starts. Your arrays start at 10 million. What does the 0x mean?
That's a hexadecimal.
Oh, that's right. That's in hexadecimal. Well, we definitely did this, no?
Yeah.
This is the R type. And we say that the R type has 3 registers and it's 5 bits each. Remember why it's 5 bits?
Because together it all adds up to 32.
Well, together it all adds up to 32, but I 7 and 12. Like,
2 to
do all
the
kinds
is
of
32. And you can put it any possible register.
because there's 32 bits. Sorry, 32 registers. So they're numbered 0 to 31. And 31 in takes 5 bits to write. The highest number, I need 5 digits to write it. 1 1 1 1 1 is 31. So I need 5 bits for the 3 registers. That's 15. The operation code, which is what function is always going to be 6. And then that leaves me 11 bits at the end, and I divide it up like this into the function, which is used to specify if it's an R type, which particular R type it is. You remember that? Every R type has a 0 as the opcode, which you could say is sort of pointless. The whole point of the opcode is to say what command is it? Is it add or subtract? So the smart engineers decided that no, we're going to put a 0 here, and then you're going to have to jump over here to see what actual command it is. So the function will work in tandem with the opcode to know what it is.
Does that make, can you re-explain that again?
Well, I'll say it in a different way. I like to, when I explain something, I'll say it in a different way. Let's talk about commands that are not the R type. If it's not the R type, I just look at the opcode and I know what command it is. Now let's say, that there are 64, let's say there are 65, I don't know, let's say there are 100 commands. Let's say there are 100 commands. There's add and subtract and there's 98 more commands. If I have 6 bits, how many commands can I specify over here? 2 to the 6th, which is how much? 2 to the 6 minus 1. Well, let's say 2 to the 6, yeah. 2 to the 6 commands. 0 would be 1, and then what is 2 to the 6? Well, 2 to the 5th we said is 31. So 2 to the 6 is 63, 0 to 63, or 64 commands. 2 to the 6 is 64. So I have only 64 possible commands here. If I have 100 commands, how can I do it? So one solution is to say, well, just take another bit, make it 7 bits over here. Right, I can make it bigger. When I design my computer, I could decide that the opcode will be 7 bits. Why not? And then I'll have not 64, but 128 possible commands. What if I want more than 128? So the idea that they say is they said like this: let's keep it to 6 bits. And for those extra commands that are beyond 64, what we'll do is we'll put a 0 here, and then we'll say use the function over here to be the other. And that'll give us a whole nother set of 64. Say, well, why didn't they just add one more bit here?
Oh, cool.
But the answer is because in some formats, when it's not a 0 here, then I'll use the function for something else. And I'll reuse those bits for some other purpose, which if you look here, wait.
When would there not
Look
be
at this button. This is not an R type. In this one, these 6 bits are the op command. So these will be numbers less than 64. These will be the first 64 commands. Really 63 because 0 I'm using to tell me to go and look it up. And then where's the function code? No function code. Why? I'm using those bits for a different purpose. I'm using those bits for the immediate value that I want to have here.
What is an R type?
If I would make this 7, what do you say? If I would make this 7, then I would only have 15 bits here. And I wouldn't be able to put 32,000 over there. I'd be able to put 16,000 over there. I want to maximize the size of this space. You asked what is an I type? For example, add I. Remember add I? Add I takes 2 registers and a number. Add I is like this. Add I, register T0, register T1, and then a number, 32,000. And what that says is, take the number 32,000 and add it to T1 and put it into, in other words, do plus on this and put it into T0. And that number, I'm limited by how big that number can be because it has to be exactly 16 bits. It can't be more than 16 bits. So I can't write a number larger. I can't write like 1,000,000 here. I could write 32,000, but not much more. So if I would have made the opcode longer, then I would have had less bits over here because everybody has the same size opcode. The I type or the R type or the J type all have the same 6-bit opcode. So if I would have made this 7, then it'd all have a 7 one. And then this would be, then I still need 5 over here for sure. I need 5 for specifying a register, 5 here. So if this is 7, 5, and 5, then I'm left with not 16, but only 15 bits. And then the largest number I could have would be 16,000 and something, which is just like a really small number. I'd like to have this as big. I'd ideally like to have this be in 1,000,000 bits. But I've got to, everything's got to fit into 32 bits. So the engineers figured out this idea that we'll say, if it's a 0, then anyway, I'm not using this as a field. It's an R type. I have 3 registers, and I don't need, and I only need another 5 bits for the 3rd register, and I got a lot of extra space. I'll use the end bit. I'll use the end area of the format to specify which command I want.
Can you show us another practical example with an R type?
Yeah. Well, I mean, the best example is here. I don't know. I'll just do it. Here's an R type. Let's do it slowly. Here is an R type. And let's, here, I'll show you in the table. Oh, actually, it's in Moodle. Here, see. Moodle. And now if I go, and if I go to Avi Treisman, he just has like, oh, what is he? Green card, see that? Now, make this a lot bigger. Here. So, first of all, look on the screen card. This is like cheat sheet for programming or for part of this course. Here's the R type, the I type, and the J type. They all have the same number of bits, obviously, 31, but they're different formats. What we mean by format is these lines are different, right? How I divide up the bits. From the computer's perspective, it's just a set of bits, but what the meaning of those bits is changes. If it's an R type, then the 3rd set of bits here over here is the register destination. But if it's an I type, then those bits are just part of the immediate value, right? And if it's a J type, a jump, then this is the address of where I'm jumping to.
So these are all just different types of functions that do different things. So the opcode for R is addition, and I is, what's the difference between R, I, and J? Meaning, what do they do besides the name R, I, and J?
Well, from now, let's just think of it as R type is called R because it's got a lot of registers. R is for register. It's got 3 registers. Okay. I type, any command that has 3 registers is an R type. That's just a rule. Whether it's add or whether it's some other crazy thing that you never thought of. Doesn't matter what it is, but the one thing that is in common is that it's got 3 registers. An I type is anything with 2 registers. Anything that has just 2 registers is an I type. And no registers is a J type. And that's it. That's it. That is the division. 3, 2, and 0.
And you'd want to try to use an I or J if you're able to, because then it'll make it faster.
No. So we have this table here. And this table, look at this R, J, and I. You see that? I mean, maybe you were right, but let me just say it differently. These R, J, this just tells me what type it is. In other words, the OR command, the logical OR command is an R type. The OR immediate is an I type. The set less than command is an R type. This is a list of all the commands and what type they are. And they're just fixed. You can't just change it around. But I mean, you can say the engineer what they wanted to do, but I was trying to explain the subtlety of why this is chacham, why this is clever. But it doesn't matter if you know why it's clever or not. You just have to know how it works. Now, if you look over here, if it's an R type, look, see the R? It has a 0 over here.
Yeah.
And then a number. Let's find another R. R, 0, and then a number. R, 0, and then a number. But look, the I type doesn't have that format. It just over here, it just has a number, 9. Why is that? So when it's a 9, what this means is that's the opcode. The computer, you put in 9 in the first 6 bits, and it knows that it's an add immediate unsigned. Put in 8, it knows it's an add immediate. But if it's an R type, then what you do is you put in the first 6 bits, you put zeros. That's what this line here means. This 0 here means. Put a 0 in the first 6 bits in the opcode. But in the right-hand side, in the function box over here, you put the second number, the 20. And that's why it says on this column heading, opcode / function. Notice this is the opcode and this is the function. So you say, well, what about this one? This one is just the opcode. It really should be opcode parentheses / function. In other words, either in this column you'll see the opcode, or you'll see the opcode / the function code. And you'll see add is 0 as the opcode. And also jump register is 0 in the opcode, but they have different function codes. So that's how you'll specify which command you mean. Yeah.
Why would somebody do add or add like versus add immediate? Like what's the benefit to doing one?
So you're asking now a different question. You're asking now about let's go over some of these commands, which we could do. But I just want to first, before we get there, I want to just make sure you understand how to translate this into these formats. Does anybody have anybody still not clear or has a question?
Go back to I just want to go back to the page.
Back to
The page where you had the
here?
different, yeah, the differences in what.
So wait a second. So based on that table, I hate those things down. Based on that table, if I look over here, I see add is 0, 20, and notice that it says HEX. It doesn't mean that a witch is going to put a hex on you. What does that mean? It means hexadecimal. So what is 20 in hexadecimal?
In what?
In decimal. Translate 20 hex to decimal. 32. Everyone sees why it's 32? Because the 2 in the 16 columns. If you remember 3rd grade math, the columns, right? It's 2 in the 16 columns. I actually learned that in like 3rd or 4th grade. They taught us base 8. This was a theory of teaching math. Now they teach math in this crazy way. I don't know if they taught you guys this.
They started a new method.
Well, I don't know. My kids are learning in a crazy way, which is that they try to get them to do things in their head. Like, 39 times 2. Well, 39 is like 40, and 40 times 2 is 80, so it's 78.
Minus 2.
Oh yeah, we did
That's
that.
I thought-
That's not how my brain works.
That is.
That's how you do things in your head. You say, oh, 30. Yeah, but then but then try to do that for 37, and then it gets more complicated. 37 is like 40,
Yeah,
but
with
it's
30
3 extra, then you
I
got
would
to
do
2.
30 times
I
2
would
and
do-
then 7 times 2.
And then
That's
add.
it.
Yeah, that's how my
together.
brain would do it more.
I can't do much of that.
Well, the way I do it is I do it the way you're supposed to. The way they taught me is 39 times 2 is 9 times 2 is 18. Carry the 1, 6, 7, and then I got the answer.
That's so hard.
No, but that's how you do it on paper. Why teach people how to?
That's not going to teach you the logic behind it.
But that's
just,
not how I do it in my
kids-
head.
Kids nowadays do that, but they have no idea what they're doing. So when they do that, they're just like, okay, this is just the rule, but then they never
Yeah.
know the concept behind it.
No, but
And
So they
I do
figure out
30
that
times 2
when they're
is
16, they figure out the concept behind it. But the main thing is they get it right.
Yeah, honestly, that's
No,
true.
but
You know, it's right. When they're 16, they'll figure out the concept. At some point, they'll
Like, I
understand
had to
it.
go on and rush through as many
Most
problems as you
stressful thing
can.
ever.
What?
Oh yeah.
I did like millions of these things when I
No,
was
they
in
had,
4th
like,
grade.
in
or whatever.
elementary
Yeah,
school, you had,
like,
like,
But
math.
my
Those
kids
are
don't
big
learn
ones.
this. My kids
Those are
just
like
learn to
big.
do it in their head.
And it was just pure.
They
I think we should have.
of the table.
I think we
I'm
should
like,
do a
I
mental
think-
minute and like see how far we get.
Oh my gosh, I have a calculator.
What is a mental minute?
You
Do
get a math
a
page
lot
with like
question.
60 different very easy multiplication problems, and you're just supposed to like run through them.
As fast as you can,
And
and when
see
the
how
minute's
many
up,
you
you
get.
put your pencil down and you get
5.7.
graded.
Yeah.
It's just to see, like, to
Yeah.
memorize, like, the
It's
times
kind of
people
intelligence. It's a kind of intelligence test, actually, because if you're smarter, you'll be able to do that.
I agree.
But you're right, but in this case, what you really have to do is if you have
I
30,
get
We do it every day.
I do
You do it in your room.
if you have this problem, you're right, you can solve it faster in your head than on paper, right? Because you can tell that it's 80 and it's just minus 2. But sometimes you have a harder one, like 137 times 3, you know.
I would go 300 plus.
But it would take me
plus-
longer, I think, to
plus
add up
90.
140
300 plus 90 plus 40 plus
than
7
to
times
just do
3
it
is
the
21.
long way. My
You're saying do
question
this,
is
do
like-
140, do 140, 140 is so 300, 420 minus 9 is.
Like, I already
Yeah, I
have
can
to
do
do paper to do what I want to do. If you add things, let's say you were adding 7 and 8, how would you bring it?
What?
If you were adding 7 and 8, what are the steps you're bringing?
I just know that 7 and 8 is
Okay,
15.
but for example, okay.
Oh, what are the steps that my brain takes? I take the 7, I take off, it takes really 5 and 2. I add the 2 to the 8.
Yeah.
I say 7. If you
Oh,
ask me,
so I- yeah,
how do you
I
add
do it this
7
way.
plus
How do you add
8?
7 and 8?
7 is really 5 plus 2. The 2 goes to the 8, and then it becomes 10,
Right, so
and
I
then
take
it's
the 3 from
5,
the 8.
so then it's 15.
I do the same thing. I take the 3 from the 8 though.
Okay.
7 plus 7.
That's how you do things in your head. Anyway,
That's so weird.
so why did I get to this irrelevant point? Because this is the ones column,
This is the 10.
this is the tens column, and this is the hundreds column. In hexadecimal, if this number would be in hexadecimal, this would be the ones column. This would be the 16s, and this would be, no.
Well, 60, sorry.
No,
we can do
no,
6.
no,
Wow,
no,
you're
no,
right.
no,
Well, but we don't do that. We never go more than
What's
2.
16 squared?
It's 256.
256. This would be the 256's column.
We usually only talk in terms of
But-
bits.
You usually do, but I usually talk in terms of everything. This, this number in hex. So look at this, this number in hex. This is the 256 column.
Plus 16 times 3 plus 1.
We'll actually go to the page right
Look,
before this.
wait. You want to?
I want to go to the I.
I wasn't bragging. I was just
Wait, are
showing
we
you.
really gonna have to know, like,
What's after 256?
Yeah.
No.
okay.
But I want to show you
Here's
one
my
thing.
fault, by the way.
Right, it's just, it's the same numbers as the.
But the only reason I know this is because of 2048. Like, so converted.
Where is
it?
It's 16 keys. The most useful thing is in high school.
Here, look, guys or girls. This number, children, attention please. This number, this is in the ones column. This is in the 16 column. This is in the 256 column, etc. So when I see a number like 10 million, it's a much more than 10 million, right?
Yeah.
Because this is not the millions column. This is the whatever column. The whatever it would
But we're
be
not gonna have to,
out
like,
there. You don't have to know that, but you just know.
Good to know that for digital.
No, you don't need to know that.
Wow.
We just need to.
I'm just explaining what a number is.
So we're just gonna have to do it, we're just gonna use.
But you will be able to, but if I want to translate this into binary, I can do it very easily because I said to you in the beginning of today that every digit of hex is 4 bits. So that number at the top there, 7 is what? 0, 1, 1, 1, right? And then I can take the F and that's 1, 1, 1, 1. And then the next F, 1, 1, 1, 1. And the next F. So I can translate this into a very long binary number from hex. To translate this into decimal, good luck. But to translate it into binary, I can do.
We don't have to do that, right?
That's
Translate
so
save
nasty.
numbers
To translate a number like that into
decimal.
decimal, no.
Oh, that's
But into binary, sure. Why not? It's
Binary's
easy.
not hard. You just.
Binary's not hard. Binary's not hard. Binary, you just have to view it as parts. You can't do that. You can't do that in decimal. You can't say, well, I'll just take the 7 and say, well, that's 7, and the F is 15. So what are you gonna do, right? 7, 15. You can't do that. 15.
I think
That would be nice, but it won't work. It's not the right number,
I
right?
think we should have a revolution. Make that happen.
It will be called the green method.
Go green.
Okay, so
Go
you
green.
can't translate directly from, there's no like easy algorithm to translate from. You have to count how many columns there are and then put this is 2 to the this is, and by the way, I want to tell you something else. You know what this really is? Error at 1, 10. You know what it really is? I can write it a different way. I can write it. This is 10 squared, right?
Yeah.
This is 10 to the,
1,
and this is 10 to the
0.
0.
Yeah.
You know
So
that.
then the next one would be 10 cubed.
The next one would be 10 cubed. But I'm saying 10 to the 0 happens to be 1.
Oh,
And
so
so it
it's
works
16
out.
to the 0, 16 to 1, 16 squared, 16 cubed. Like, it's the same thing.
Okay, so let's
Can we do to explain what
So we're
constant or address offset to?
wait. Let's still with your first question. What's your name?
Shlomi. I'm sorry.
Shlomi?
Sorry.
Shlomi what?
Bernstein.
Bernstein. Okay. So Shlomi was asking you what about this. So let's do this one again. This is a add. So if I go over to this table, I'm gonna see that add is 0, 20. And we said that 20 is really 32.
32.
And what does it mean 0, 20? The opcode is 0 and the function. So I'm just gonna plug this into my format. My format is R type, so opcode function.
Okay.
So here I'm gonna put a 0, and here I'm gonna put the 20 in hex, which is 32. So look, here's the 32, and here's the 0. Now I know it's an add command, right? Now the computer will see that and know that it's an add command. Now I have to translate, so I've translated this part. All the information that's contained in that word add has been translated. But this information has not been translated. I gotta translate that. This pound symbol is a comment. Anything after that is a comment. So I just have to translate this information. So so I'll start with the S2. S2 is has a value. It's a numeric, it's really a name of a register. There's only 32 of them. All the registers have numbered values, 0 to 31. So I just go over here, and on my same green card, it has very conveniently written for me in a very concise way, all the register names, see name. This is register name, number, use, call, convention. Use just means like why you use, what is it conventionally used for? Call convention, oh, that's interesting. Preserve the first call. That's like my function calls. I never actually thought about what this column is. But yeah, it's not really that important. But preserved across, oh, wow.
Oh, yeah, it's so interesting.
It's so
Fascinating.
interesting.
What does that mean? I just see a bunch of.
You don't need, yeah, you
I also
don't, you,
understand that.
when you learn about functions in the lab, you'll learn about it. Okay, so wait a second. So what does this mean here? A0 is number 4. What is A1?
5,
What is A3? 7. Okay, that's what that means. 0 to 7
It's like a trick.
is it's a trick question. I'm trying jumping your mind there a little bit. What is T0?
Temporaries.
The
No.
number.
What is T8?
Non-existent.
Non-existent. It goes to T7.
Oh, no, it doesn't.
Oh, I think it
Temporary.
does exist. Look at that. It's down there. Somebody was really trying to play with you and put the T's, divided them up.
Why?
Why did they do that?
Why did they do that? I don't know, but I like it for one reason, which is easy for me to remember that T0 is 8 and then S0 is 16. It goes up by 8.
Do you know what T4 is?
What's T1? Let's start simple. What's T1?
9,
What's T2?
10,
What's T4?
12.
12.
It's a thing that happens when
We were
someone
waiting.
brags, but, you know.
Subtle brag.
Subtle bragging.
What's subtle brag?
No, there's just there's like a Jewish joke about T4 being like a subtle brag.
I don't know what T4
And
is.
it's just
It's called a T4.
it's called a T4, so that's fine. Just,
It's not
No
important.
idea.
Use it in a sentence
so
now.
the nerdy way of doing this.
Okay.
I'm T4ing as I'm doing.
Okay, so everyone understands that there's a translation, numerical translation for what is S? So S0, let's remember, is 16, and T0 is 8. If you just remember those two, you already have a sense of the whole table.
Will we get this on?
Yes, you'll get this on the exam.
That is so
If I have anything to say about it, you'll get this on the exam.
Wait,
Thank
the
you.
T0 is
Something
8 and
What?
S0 is what again?
16.
Well, it's written here. S0 is 16 and T0 is 8. Let's just, I mean, you don't have to remember this whole table, but it is actually convenient if you remember those two. And then you come over here And I see S2, should what number that be? What number should that be? S0 is 16, 17,
18.
18. It should be 18. And look, lo and behold, here is that 18.
Oh, well.
It's a good way to cheat.
Now, this is, but notice the order switched. I talked to you about that before, right?
Yeah.
Yeah.
The order switches, so remember that we start with this T0 is going to go all the way here. T0, remember, is 8. And here's again T0 because there's 2 T0s over here. So that's it. 0, 18, 8, 8. And then this shared address we're not using right now. It's just like unused.
That's 5 bits also.
That's 5 bits also. And this is 6 bits. So now ignore the other lines. Let's just look at this one line. 0, 18, 8, 8, 0, and then 32. Remember what the 32 tells us that it's an add. Now, if I jump down over here to this middle row, here's the 0. Here's the 32. That's 32. Here is the 8, right? That's 8. 1, 2, 4, 8. And that's 8 again. And this is 18.
So is that
Right.
what, is that like, you put in like the top and then the computer translates it to this?
No. The assembler, essentially the computer, in the end of the day, the computer is going to get this. And that's what we said, that the computer understands ones and zeros.
Mhm.
The computer just understands ones and zeros. I'm going to write my nice little nifty add T0, S0, and I'm going to write it in names and name the variable, name the registers and calling it, instead of calling it register 18, I'm going to call it register T0. It's like a little bit easier to remember. And I'm going to use the word add. But in the end of the day, the computer is going to get just ones and zeros. And based on those ones and zeros, he or she, I don't know if computer, some computers are male, some are female. Some are gender and unknown. Gender confusing. So the computer will, I think in Star Trek they refer to them as she. So the computer will, she will know what to do based on this number.
That's because they look at it as like assistive robots.
Okay, you're here to serve you.
Yeah.
Perfect. Love that.
That's what, you're saying because they serve, therefore they're women?
We're really gonna get to technicalities here.
Okay, so everyone understands this line? Yeah, any questions? We're sort of repeating what we did last time, but it's good. Now, by extension, it's the same thing for the other one. But let's see, Shulamit, be with me.
Sorry.
I know your name, so
I know now. I've
now you're
messed
cursed.
Everything.
I've messed myself over. I've
Yeah.
just too much.
You should have given me the name of the girl sitting next to you.
This one or that one?
Either one.
That one.
Somebody. Okay, so I had a class with last semester I had a class, the year above you, it has 3, or 2 years above you, it has 3 Shiras.
Wow.
Oh, yeah.
Right?
Shira Feldman
Shira
and-
Feldman.
Who's the last Shira?
Do we dropped out?
Maybe she dropped
I
out.
don't think we have
Nobody
Mama
dropped out?
Feldman.
Maybe just 2. Maybe there were just 2.
It was Shira Feldman, Shira Feldman for sure.
Yeah.
We don't have any two.
But there could be another
So I
one
started
that
calling all the girls Shira. And like,
Then
It
you're
was
good
probably
to go.
one. We can all be undeniable. Don't we have like 4?
okay, so load word. What type is load words? Based on the rules that I told you today.
It's a register. I made that up.
You're wrong.
It's
Not,
It's 2, so it's an immediate.
It's an immediate. It's 2. It's an immediate. So it's 2. 2 registers. I only see 2 registers there, so it's got to be an immediate. Why? And in fact, it makes sense that it's immediate because I see this thing here. What is this? That's not a register name. What is that?
That's an immediate.
I'll give you a hint. It starts with the letter N. It's a number.
oh, it's a number?
That is a number. That's a number. Whenever there's a number in the command. I'm serious.
Too hard about that one.
It's a number.
It's a number. It's just a plain number.
It's not what
It's actual number in decimal. It's a number. It's in the command, that number. It's kind of weird. You usually think of a command would have registers in it, but this is an immediate command. Therefore, all immediate commands have numbers in them. That's what immediate refers to, number.
These are in the L format?
There's no L format. Unless you call it I.
I,
Unless you
I
call
format.
lowercase L an I.
I format.
The reason why load word we can do faster because we're just loading the word. We're not doing any addition. There's only 2 elements in it, so we can do it faster.
Well, first of all, what's faster? Did you say faster? No, look. There's lots of I's. Let's look. I. Load
Right.
word is just one example. Don't get
Let's go
fixated
with-
on that particular example. Look at all these I's, all these different I's here.
But it looks like the functions of like adding and subtracting, they usually are registers, but those.
No, but there's gonna be an add I. There's gonna be an add immediate, which takes 2 registers and a number.
Oh, because it just as adding this into that and instead of this
Mhm.
plus this into
Exactly.
there.
I wrote there, that add I.
Oh, now I'm getting what's.
There's a number. There's 2 registers and a number. So it's an I type. This load word also is 2 registers and a number.
Instead of.
The number has a different meaning. We're not adding that number to anything. Well, we are kind of adding it, but what is load word? Load word means take something from memory and put it in a register. Take data in memory and put it in a register. In order to take data from memory, I have to know where in the vast memory of the computer it's located. We call that an address. I need the address. The address will be stored in T1. We're assuming that. I'm not explaining to you. In the lab, you'll learn how to put an address into a register. But assuming that the address is in that register, what I want to do is I want to go to that register, then go to from there, offset 1,200 spaces. Offset, you understand offset? Like index, but I call it an offset because offset means how much you're off the beginning. The set, like, is the beginning, like, ready, set, go. So the set is like the starting line. And off is how far you are advanced from that point. So it's called the offset. So the offset here is 1,200. And that is the 3rd field. Remember we said that that the format of an I type is that there's a number here. And it's 16 bits. Can 1,200 fit in 16 bits?
Yeah.
Definitely, right? We said the largest value is 32,000, plus or minus. So 1,200 can fit. So that's what I'm doing here. This 1,200 here is the translation of this 1,200 in an I type, and it's actually taking up these 3 columns. I wrote it only in the right-hand column because I couldn't erase these lines. But really imagine that this is extending all the way to here. That's the half of the command. Remember, the command is 32 bits. The 16 of them are just for that number. We want to maximize that space for the number so we can have a large number. Then I have 5 for the 2 registers, and 35 is the opcode of load word. How do I know that? Opcode of load word, that's store word, load word, 23. 23 is not 35.
32.
It is
It's
35.
32 plus 3.
It's 32 plus 3 is 35. Yes. What's your name?
Maven.
Maven?
Maven, yeah.
Like Maven or? Yeah. Okay.
About the command before, it said T0. When we were loading the word, what were we loading into T0? Were we loading the address or were we loading the value?
Into T0
Because in the
here?
next command in add, it said it's putting the result into T0. So is T0 the address or is it the value?
Yeah, well, you're saying we put something here and then we immediately overwrite it.
Right.
But,
Meaning,
but we don't immediately overwrite it because we took it here, we got it. How does this command work? It's add. Take this, which is the value that I got, this value goes over to here. And then I use it and I add it to TS2 and then I overwrite it. Well, that's exactly what I'm doing over here. You see, look, I'm overwriting. I mean, it's not the same overwrite.
we're putting the value that we got, the new value that we got of the 2 added numbers, we're putting it into T0. Oh, and then the next line is store word.
I mean, I could
Never
have,
mind.
yeah.
I didn't see the next
The
line.
next line is copy that and put it back into the place.
Oh, okay, that's my question.
Yeah. The truth is, maybe you weren't asking this, but I could have used, instead of T0 here, I could have used any other variable. I could have used like T3. I could have wrote T3 here, which would mean take with the value that I got, add it to S2, and then put it to T3. And then and then I'd have to write T3 over here, take T3 and load it and store it back into memory, right? I just chose just to be clever, I just used the same variable again, because I could. So that's the translation here. Notice the 9 is the where are we? Is the T1 over here is the 9. Notice it switches.
Right.
And the T0 is there. So pretty much it always switches.
It always switches?
Yeah, it always switches.
Only for the registers,
Only
not,
for the registers.
not the number. The number is still.
No, but I mean, the 9 is here second. Here,
So it says 1200 and then TI. The 1200s are the function. All the way at the end.
well, the 1200 has to go over here because that's the space for it. Yeah, I mean, that's the end of the second half of the command is always the intermediate value, so the 1200 goes there. This is the index, of course, is outside of the parentheses, which is kind of weird, but because you're used to C++. So that's it. Is that clear? And then we go from these decimal numbers to the binary numbers, and we have full binary programming. In other words, that would be what the computer, when they used to have these punch cards, that was what was on the punch cards. It was ones and you would punch a hole here. That means this is a one. That means on what does it mean? Well, it meant like, I don't know. There was, I guess across the card there were ones and zeros, and wherever there was a 1, you would put a hole, and then you'd know there's a hole. No, they have a machine. You type. They'd have punch code punchers. First, you would run your program. I never did this. I'm not that old. You ran your program through. It was finished. Let's say you ran it through a punch code puncher, and it would just punch the holes according to your numbers. Then you took the cards downstairs to the computer and you fed them into the computer. So you didn't actually have to punch it yourself. But you did have to, but you had a punch code puncher and then a punch code reader. Kind of dumb. You could just put the code directly in. Okay. This I'm going to leave to Avi to teach you. This is how to getting a pointer to an array. How to actually do that. This is a loop. This I'm going to skip also. System calls. This is how to read in, read out variables. Here's a JType though. JType is important. I'm going to explain it again. Did we talk about a JType?
Only for a split second.
Only for a split second. Opcode. So a jump. So here, I like to teach you C++ at the same time as I teach you this, because then I believe that's the way the brain works. The brain needs connections between different things. Okay, you've learned this. Now let's add something into that. So to make a loop in a for loop, and then what tells you to go back to the top? The fact that there's a brace at the end, right? The brace at the end tells you, oh, now go back to the top. And then it checks the condition and either breaks out. So this is called structured programming. Why is this called structured programming? Because it's a structure. The brace and the close brace is a structure. And through the structure, I know what to do. But let's talk about unstructured programming. What would that be? There is such a thing, and that's what existed before structured programming. So what is unstructured programming? Unstructured programming still exists. It is backward compatible in C++. In other words, C++ allows you to do unstructured programming. What would it be? You would do like this. You do like int I equals 0. If I is greater than 10, then go to end. And then I'd write end over here, colon. This is actually illegal in C++. Go to is a one word, no spaces, and it means jump to. So go to the end. If I is greater than 10, jump to the end. And then I could do I plus plus. And then I need another label. I'll write a label over here, start. I could call it end and start, or I could call it anything I want. And then I'll say, go to start. And this will jump to here, check the condition. If it's met, then jump to here. If it's not met, it'll keep going until eventually I plus plus will be greater than 10, and then it'll go to end. So that's an unstructured loop. That's a loop with go to. And there's an article written in 1970s called GoTo is dangerous. And so since that article, people say don't program with GoTo. But there is such a thing. And there are cases where a GoTo is useful. When is a GoTo useful? If you have, let's say, a loop within a loop, within a loop, within a loop, within a loop. And if a certain, you're 6 levels down in a loop. And a certain condition happens, you want to get out of everything. So one way of doing it would be changing a condition in every single loop, that if that condition meets, then the inner loop will break, then it'll go to the outer loop. And then that condition, you understand what I'm saying? You'll have to add that condition now to every single loop, so that when it breaks out of this one, it'll also break out of the other one, and also break out of the other one, and also break, because it'll check it. But now you're checking that condition every time you're doing a loop. You're always checking that condition, which is wasteful. It takes time. So a simpler solution is if that condition happens in that inner loop, just go to the outside, just break out. And then a GoTo is much more efficient. So GoTo exists, but okay. So that's C++. So in what's it called? In assembly, we don't call it GoTo, we call it jump. Because it is like a jump. I'm jumping to here. But we have the same concept with labels, and we have, so that's what a jump is. A jump is essentially the name jump and then a target. What is a target? Target is an address. What address to go to? Because really labels do not exist. Labels are a fiction for programmers. What does exist? What does exist? Well, according to that table that I showed you, the code section of your program is in memory location 400,000 in hex. So this line of your code, your first line of your code, I mean, this is not be exactly C++. This is C++, but imagine this is assembly. The first line of your, because really, right, if I put it as an assembly, it would be more lines, it would be different. And int I doesn't exist, but let's just say it's assembly. This will be 400,000 in hex. That would be line 400,000. This would be line 400,000 and what? And 4. Very good. Whoever said 4, not 1. 400,000 and 4. Because remember, every command takes up 4 bytes. So in terms of bytes, I'm at byte number 4004. This would be 4008. This would be 400,012. And this would be 400,016. All right. And this would be, and then the end would be like 400,020. Okay. So then what I'll actually do is I'm not going to go to start. I mean, the labels when you're in the lab, you'll use labels. But here, in actuality, the labels get converted to an address. So really what this is go to start. So it'll actually be go to 4004. And this will be not go to end, but go to 400,020. Well, I wrote this as though it's decimal, actually, right? I made a mistake. This is not 12, but this is what? C. And this is not 16, but 10. And this is not 20, but 14. That's confusing, but that's the way it is. Right? So check my math. Maybe I'm wrong, but right? Everyone understands the idea? Go to end, that's this line, 4014 in hex. And this is go to the start, which is 4004. 400,004. Yeah.
It says it in 6 bytes.
What?
Like, how do you
Oh, what's your name?
Karen.
Karen. So Karen says, oh, that's my favorite question she asked, which is, but these addresses, how many bits are they? They're large numbers. They can address all the memory of the computer, which actually is very large and actually takes 32 bits to reference. And yet I only have 26 bits here. Is that what you're asking? I only have 26 bits, but I have to actually squeeze into a 26-bit address a 32-bit address. And sorry, squeeze into a 22, I said that, I'm daydreaming. A 26-bit space, I've got to squeeze into it a larger address, a 32-bit address. It's kind of like I got to put a square peg into a round hole. I've got this round hole and I got to get a 32-bit address. Why do I have to have, you're confused why a 32-bit address?
I understand, I mean, you're calling another.
In other words, this address could be anything in the memory. If this jump is going to work, I've got to be able to put any address that I want here. And the addresses are 32 bits long. That's how large the memory space is. In other words, we have memory from 0 to 2 to the 32th.
Maybe code only is like in certain parts of the memory, so it only goes up to the computers. Like it doesn't go past.
Oh, right. So Maveen says something interesting. She says, well, the code is only from 400,000 to 10 million. Maybe in that space I could squeeze it in. So it's kind of true, except that that picture that I showed you is really just a convention. In other words, it's just like an assumption. But in reality, the chip doesn't know. The chip has to be built such that I can jump to any address. Because remember, the operating system is at 0. And the operating system is also a program. It's also a code. It also has jumps in it. So theoretically, it's a theoretical problem. I do actually have this problem. And we'll solve it. Essentially, but you see why I call putting a square peg in a round hole? Because it's like, how do you get a square peg in a round hole, by the way? What? With a hammer. With a hammer, a very big hammer. You just keep pounding it and it goes in. So that's the way an engineer solves a problem. You see, that's the way an engineer solves a problem. You just, no, I just was watching, I was watching on YouTube last night. I don't know why I was watching this, but I was watching a documentary about the 747, the airplane. There, you know, 747.
Like landing on the water.
No. That's no. The design, how they built the 747.
I'm so curious.
It's actually an amazing plane. I always love this plane. Have you ever been on a 747 with 2 floors?
Yeah. What? I love it. Yeah. The older
2 floors.
flights used to all be like that.
Yeah.
Never been on one?
Not that I remember.
Two aisles. 2 aisles.
Yeah.
3, 4, 3. And then there's a staircase. It used to be a.
There's a staircase.
Yeah.
Now it's
I always
pretty,
wanted to be
it's
a
like
flight
a-
attendant.
True.
Yeah, it's only
I
for the flight
always wanted to
attendants.
go up there and I, for some reason, never got up.
I one time like walked 2/3 of the way up and looked, but I never actually went.
Wait,
I'd
who
say
airplanes
that-
shouldn't have.
I think
Was
was
it
it
like?
And it was a spiral staircase when I went up.
Oh,
Was it
no,
like-
not the
like
one I
the
went.
first-
I
Oh,
was
the
like,
spiral staircase?
Was it the first
What
class
is
people?
this?
or the-
It was for first class. The first class was allowed up. It was the first class lounge.
Yeah.
It was not just the seat. The seats were downstairs, but the lounge was upstairs.
Oh,
So you could go there, and there was a bar and a piano, and yeah.
That wasn't the 747
What?
I was on.
I can't tell which part of this is.
Not a pool, but an open bar. Not an open bar, but a paid bar.
I used to dream.
Maybe it was open bar.
I used to always feel like I was American Express.
Yeah.
I used to dream.
So anyway-
Those
I
people
existed
don't
on
complain
the plane
about
for a
how
while,
long.
like there was like showers.
It's a great plane, but it's going out of business. It's going out of use because it's a little bit, I don't know, it's not quite as fuel efficient as the more modern ones. Anyway,
The Dreamline's a new one.
you have new ones. They have 787, they have
What is that?
Anyway, what does that have to do with anything? I was watching this documentary, and in the documentary, they were talking about how it had an engine problem. They had Pratt Whitney. Pratt Whitney is the engine company. Boeing didn't make their own engines. They bought them from. And the engine was having a problem. It was designed for this plane, but it was at certain speeds, it was burning up. It was having a fire. And it was not good.
Wait, so is this like proof why you shouldn't outsource and like you should
That's like an issue.
Well, it took them a while to convince Pratt and Whitney to fix the engine, but in the meantime, they had a scheduling issue. They were going to go bankrupt if they couldn't get the plane out on time. So they just put the plane out anyway. And what was this? Now this is not. So what is the engineer? So remember, we're engineers. We have to solve a problem. We can't change the engine because by the time we get the new ones, it will be too late and we'll be out of business. So what they did was they figured out. Well, they figured out that if the engines are only working up to 50% thrust, then it doesn't have a fire. So they just change the dial, change the knob, doesn't let the pilot go beyond 50% thrust. In other words, they just made the engines work at half speed.
Interesting.
The same engine, they just won't allow the pilot to push it all the way up to full speed. And it still flew fine because they had 4 engines.
I feel like you're
and-
really trusting humans there. Like,
No, I just added that they didn't let the knob. I don't know exactly how they prevented it, but I assume they just didn't allow. I mean, maybe they told the pilot don't go to full
I'm just
thrust.
like imagining
but-
the pilot sitting there being like, I just want to go full. Like,
I could just imagine the pilot being like, I know.
So it took, so after
You
a
know,
few
people are
weeks,
like, I know
after a
my
few weeks,
car.
the pilots realized that something was wrong and that this is
did they
nothing. That,
recall it?
and anyway, the engines were sometimes failing. But but the plane was designed to fly. The plane is. This is why I like the plane. The plane is what's called over-engineered, which means that it has 4 engines, but if 3 of them fail, it'll still fly fine. In other words, it can fly on 1 engine.
Okay, so in like 20 years, when someone asks me where my trauma about flying comes from, it's gonna be this class.
Why? No, this is exactly
I'm
opposite.
afraid the plane's gonna
No,
burn.
the point is it's not because there's so many.
Because the engineers over-designed it. They built 4 hydraulic systems for the wheels to go down. That means if any one of the systems is powerful enough to put the wheels down. So that means if 3 of them fail, it'll still work.
How
It'll
did
still
it
work.
take a
That's pretty
couple
good.
weeks for the
It's the
pilots
best
to
plane in the world.
realize something was up?
Hmm?
How did it take a couple of weeks of flying these planes for the pilots to know something was up? Like, shouldn't they have like been
It's a little
either
scary.
A, informed immediately, or B, on the first to go, know something was wrong?
I don't know. But you're right. It's interesting. But what's my point? My point is, if we are engineers now. We have to solve things like engineers, which means that you make it work. Given limited resources, you still make the thing work.
Right, but if someone told you you're not allowed to drive your car past a certain speed, wouldn't you either A, ask
Get a
why,
new
or
car.
B, figure out?
Yeah. Yeah, my car won't go past a certain speed. It's not like if I go past a certain speed, the engine will start burning. It is a little bit scary. Okay, so let's go on though. So that's the jump command. I explained to you now very clearly what the jump command is and how this address really needs to be larger.
You didn't say how we solved it.
I didn't say how we're going to solve
By
it.
brute
We're going to solve it, well, not by brute, well, we're going to solve
Shove all
it.
the numbers into the
The
register
hammer and crash your.
Before we solve it, I want to just explain a couple of more commands, or one more command really, or maybe a couple. It's called the branch command. The branch is also a kind of jump. Now, this jump, if you notice, there's no condition here. This is the regular jump is what's called an unconditional jump. This is the unconditional jump because there's no condition. It just means if I see this opcode for jump, then take this rest of this and jump to that location. No matter what, no conditions. But I don't want that. I want to have in my program, if something is, then jump. In other words, how do I do, I want a jump that incorporates an if in it. So we call that if jump. We don't call it a jump, we call it a branch. And it's a special command, branch in the sense that the branches of, if a road branches to the right or the left, that's a branch. It's because it gives me 2 alternatives. So a branch, there's 2 branches, branch if equal and branch if not equal. You can ask, well, what about branch greater than, branch less than? So we have solutions for that, which you'll learn in the lab. But for now, all we actually need is branch greater than and branch less than. But this is an I-type instruction. If it's an I-type instruction, that means it's got 2 registers, right? And 16 bits. True? It's got 2 registers and 16 bits. Let's see an example of a branch. Here's a branch. This is a branch with a label. Branch not equal. If S3 is not equal to S4, then jump to else, to the else line. That's what this line means. Notice that there are 2 registers, so it's an I type. True? Where's the number? We said there's got to be a word that the word begins with N, number. Yeah.
You're gonna repeat how we read this sentence?
How we read the contents?
Yes.
Well, this means branch. If S3 is not equal to S4, that's the NE, branch not equal. BNE, branch not equal. If it's not equal, then jump to else. We also have a BEQ. I didn't show you here. BEQ is branch equal. BNE is branch not equal. So
This is an I type because there are 2 registers.
exactly.
There's no number.
This is an I type because there's no register. But you should now ask me, but there is no number here.
0.
What?
Then it would be 0. No, it's not jumping at all. Meaning if there was a number, then it would know where to jump to.
No, if they're not equal, then jump to else. I need to tell it the address where to jump to, right?
And what if the word jump?
Oh, interesting.
What?
Oh,
What if the jump in the sentence? And
Where's-
how you jump to else?
Because I did BNE. It's a complicated command. It means jump if the 2 registers are not equal.
But you put and jump.
Yeah, it checks for non-equality, and then it also jumps if there is non-equality. If there's equality, it does nothing, right? In this case, if it's not equal, if it is equal, then it'll just do the next line of code. It'll just go on. But if it's not equal, then it'll jump to the line labeled else.
and
Yeah,
else is like.
If it's an I type, then how is it a J type?
it's not a J type. It's not a J type. J types have a format like this, no registers. It's not a J type, it's an I type, but it functions as a jump. You're right. It's not a jump, it's confusing. It's confusing. It functions like a jump. That's why they don't call it a jump. They call it a branch.
Okay.
They don't call it a jump. It's not a jump. There's actually, that's even worse, though. There is something called jump register, which is also an I type. Whatever, you're gonna learn, there's other commands. I'm not gonna teach you all the commands right now. But in fact, Avi's not gonna teach you all the commands. You're expected to be able to read the script, the manual, and understand what the command does. But he should explain to you what a jump register is. Anyway, it's not really a jump, but it does a jumping behavior. It has a jumping behavior. It jumps to an address. But
Wait, so it does jumping behavior, but it's not a jump.
It's
that's
not.
right. It's not technically a J type. It's not a J type.
Okay.
It's an I type. How do I know it's an I type?
There's 2 registers.
There's 2 registers. Have you ever noticed that Arab women wear a necklace with a map of Israel on it? Have you ever seen that?
No.
I've seen that. And I was like very shocked when I saw it. I was like, what, they're pro-Israel? And then I realized, I looked carefully at it, and I asked one of them actually, like, what? And I looked at it, and there's no Golan Heights. In other words, it's not a map of Israel. It's a map of Palestine. But the whole country, except for the Golan. Because the Golan, it's also a thing I just found out just this year. I didn't know this, which is that I always thought the Golan is just like the West Bank. The West Bank we captured from the Jordanians, and they had taken it from us. They'd taken it from original Palestine, and I thought the Golan was taken by Syria. It's not true. The Golan, ever since Syria was created after World War I, was part of Syria. Under the British mandate, the Golan was part of Syria. So the Golan we completely stole. We completely stole that from Syria, and then we annexed.
But it's ours.
But it's not. But we had to. We had to. Otherwise, that they actually would, according to the mandate, they were actually on the Kinneret. Syria reached all the way to the shores of the Kinneret.
That's not good.
Well, we didn't mandate anyway. We got what
I'm just saying, in a sense, we have more legal right. We have much more legal right to the West Bank than we do to the Golan, legally speaking.
Oh,
Because that was never a country. It was part of it was part of mandatory Palestine. Then there was a division plan. The Arabs rejected it, and then Jordan took it over. Jordan had no right to take it over. So when we took it from Jordan, we were taking it from a Gonev Meganav Patur. We were taking it from they were Ganavim. They had no right to it. The Palestinians didn't have it. The Jordanians took it. They had no right to take it. So when we took it from them, we were taking it from people who shouldn't have had it anyway. But when we took the Golan, we actually took it from people who should have had it. I mean, I personally think we should take the Golan, we should take back the Sinai, and reconquer Gaza.
Ambitious.
That's my personal goal, but I don't think I'll execute that goal. Anyway, but I'm just saying, I never realized that the Golan, but now nobody even thinks of giving it back, because who would we give it back to? This country that's in the civil war anyway. But it's very interesting, apropos of what's going on now in Russia taking over Ukraine. You just read about that, I'm sure.
Yeah.
Which actually, they actually have a justification.
Because they think it's been theirs the whole time.
They think, no, because the Ukraine, was never a country. That's what Vladimir Putin said. He said it was never a country. It's true. When was Ukraine a country? It was part of the Soviet Union. Before that, it was part of the Russian Empire. It was never a country. And the part that he took, actually, they speak Russian there. In the rest of the country, they speak Ukrainian. But in that part, they speak Russian.
You actually took it?
Oh yeah, he took it now.
Oh.
He took-
I missed that.
He took
that part of it.
that part. He took the eastern part of Ukraine.
Oh, so it's
The
like
part
Russia's
right
now?
But not a war. He said he wouldn't attack by war because it's not a war. What he did is he just said, I recognize that area which already had been in a rebel state as being a country. And now it's a country. And as a country, I'm going to help them. They asked for help. I'll just drive my tanks into their country because they want me to come
But doesn't that,
in. It's
and
not a war.
that was just accepted.
And that was just accepted because what are we going to do? What is America going to do? You're going to go send thousands of troops and start battling Russians
But that's not
for
Kiev, right?
the Ukraine? Not Kiev, but just a small area. There was a small area of the Ukraine that was already under Russian dominance, whatever.
Oh.
So it's not really. It's just a tech, but it means that they're rolling tanks across the border, which they hadn't done. And now they're saying it's not war. It's just rolling tanks. It would be
Isn't
just-
the greatest tragedy that happened in the past 100 years is that the Soviet Union fell?
who said that?
Putin.
No. Who said that?
Putin.
Who?
Oh, I
Oh,
say
Putin said that.
Yeah.
Are you saying it in Russian accent?
She's saying it correctly, none of us
You're,
understand.
what? You're
My parents are like originally from the Soviet Union.
from where?
Well, my mother's from Odessa.
Uh,
My father.
Odessa's Ukraine.
Yeah.
And your father?
So it's like fun. My family chat's going nuts about this whole
Yeah,
thing.
Yeah. What did he say? So Putin says what?
He said that the biggest tragedy that happened in the past 100
Yeah.
years is that the Soviet Union fell, so he's trying to build it up.
He's
again.
trying to build it up, but he's doing it differently. He's trying to build up he's trying to build up the Tsar Empire, really.
Yeah.
He's doing exactly what Russia did for 500 years, which is take over little pieces more and more and more. But what is America going to do? What are we going to fight a war? We can't do nothing. Nothing we can do. There's nothing anybody can do. The only thing to do is to give the Ukrainians weapons, which is great for America because we like selling weapons.
Rolling
like,
tanks
Americans
into
don't
somebody's
do that.
country is an act of war.
Not if they ask you to bring them in.
According to you, Nathan.
No, according, no.
No, if the country.
According to you.
No, what they did was a clever thing. What they did was a clever thing. They said, we're not putting train tanks into Ukraine because this region of Ukraine is not Ukraine. It's a country.
Russia.
It's not Russia. It's a new country on the map. It's a brand new country called, what is it called? You know,
Like, are you talking about?
Do-
Yeah, but that was a while ago.
Duhets or something?
No.
Oh, they called it something.
No idea.
They
On
gave-
maps,
look
it's
it
called
up.
Donbass, but like I don't know if that's real.
Yeah, maybe Donbass, something like that. It's this new area. It's a new
Everything's
country.
in Russian.
It would be
Donetsk
like if
and Luhansk.
what? Say-
Luhansk and Donetsk.
Luhansk and Donetsk. That's the name of the country. So it's a new. We just say.
And
Brand
Brand
new
new
countries in like the
countries.
past few days.
It would be like if we would say the settlers. We're not. Well, that's a bad example. I don't know. What would it be like?
It would be saying that the Golan's not.
It would be
part
like
of
this is
Israel.
what they should have done. It would be like they would say like this. Well, remember, I don't know if you remember that Israel had this southern Lebanon, where there was a 10-kilometer air region of the southern Lebanon that Israel was in control of for 20 years. And Ehud Barak took us out of Lebanon. But we were controlling it, and they were all Christians there. And the Christians were happy that the Israel people were there. What we should have done then is say, Israel recognizes southern Lebanon as a country called Southern Lebanon.
We're not leaving them.
And then we're not occupied. They asked us for tanks. Since we're not occupying it, it's its own country, and we're just helping them defend themselves from northern Lebanon. That's what's just announced that this is a country. Anyway, there are many countries like this. You know that there are many countries like this. For example, Northern Cyprus is a country recognized only by Turkey. And South Ossetia in Georgia is recognized by the Soviet Union only as a country.
And they have dominion over them.
Yeah, exactly. They recognize it as a country, and then that country speaks Russian, and they get help, military assistance from Russia. But it's its own country. But only Russia recognizes it as its own country. Georgia believes that a portion of their country has been stolen from them. I was just there actually. I went in between the semesters. I went for 4 days to Georgia. Beautiful. And I went like probably 3 kilometers from South Ossetia. I was just like on the border of I was right, like South Ossetia is like this, and I was in Georgia, but South Ossetia was beneath me and to the left of me, and Russia was above me. That's where you go skiing and skiing. Yeah. And then the Russians is very interesting because the Georgians really don't like the Russians because the Russians took over, a quarter of the country. But the Russians go there to visit for tourism.
Even the Russians.
So they speak
Yeah,
Russian,
like-
but they don't really like the
I
Russians.
feel like that's not such a novelty because they don't like them.
That's so
Like, they don't not
funny.
like even like the Russians. I said even the Russians don't like the Russians.
She's like offended. No, she's like, I don't like it.
Anyway, all right, let's continue on in our technical study. So everyone understands what a branch is. And I'm about to explain this else. This else is a problem because this else is a label. And as programmers, you can use that label and that's fine in the lab, you'll do that. But really, what should it be? A number. It should be a number like any other I type. An immediate value. And how many digits should it be?
2.
How many digits?
16.
16.
Oh, 16.
16 bits every time. Every immediate, the number is 16 bits. And how big is the address that I'm supposed to jump to? 32 bits. Now I got to fit a triangle into a round hole. In other words, now I've got a harder problem. I got to have 32-bit address in a 16-bit space. How am I going to do that?
You drag it by the corner and you make it smaller.
So we have two problems, right? We understand the problems, but essentially this means jump to an address. And the address is only 16 bits, even though addresses should be 32 bits. I'm just explaining you the problem. And now.
So you convert it into a different language, solve the problem. From there, convert it back into assembly. Convert
Okay.
it into binary.
The rest of this, I'm ignoring you, but the rest of this is.
Okay, everyone does.
I mean, I wasn't ignoring you.
So
I
we're
said
done
I'm
with that
ignoring you. I'm
PowerPoint.
like, all right, let's go on. Okay, so everyone understands the problem. Keep those in the back of your mind. Either we'll get to it today or we'll get to it tomorrow, next week. Hopefully today, though. I don't know how much time we have, but we got to go faster a little bit. Now I'm on lecture chapter 2 and 3. Each command must be stored in the processor's RAM, right? That's obvious to you in memory. You said that. I already said that, like here, it's in line 400,000, 400,004, etc. There's something called a special register called a PC, which is called the program counter. And it tells me what line I'm currently executing, or actually it tells me the line I'm about to execute. So in other words, the PC will have the value 400,000, and then I'll execute this line. Then immediately the PC will go up to 4004. And then when I finish executing this command, I'll already have a 404, and I'll be able to execute that command. Now, what happens is the PC, even before I execute the command, it increments by 4 automatically. Okay? So the PC will keep incrementing by 4, and that's how I will progress through the program. If you think about what is a jump is
It could be
changing the PC. Instead of it being +4, if I want to jump backwards, it should be -16, right? I'm just changing the PC. The PC is telling me what's the next line to execute. So normally it's going to go up by 4, but on a jump command or a branch command, depending on whether if it's a branch command, then the condition could be true or not true. But if the condition comes out to be true, then I won't jump. I won't go to the next 4. I won't go 4 ahead. I'll go whatever the address is. I'll change the PC to the address.
So we're overriding the PC when we do a jump or branch?
Yes, exactly. We're potentially overriding it. Depending, if it's a jump, then we're overriding it. But if it's a branch, then we're potentially overriding it. Because if it's a branch, it's a condition. Is, not a. Yes,
And is this like automatically in, or we need to set it?
no, this automatically happens. This is happening by the computer is doing this. Okay. The computer is doing this.
What is the computer that we so speak of?
What we're going to learn about.
Yeah. I never understood, and I think we're getting there. I feel like we keep inching way.
Yeah, we're getting there. We're getting there. You will understand it. Every digit of the hexadecimal corresponds to 4 digits half a byte. Remember we saw this? We all know this is A. This, the part of this, the 4 first bytes here are A. and this is C, so it's AC. Here's the I format. It's just, I'm sort of repeating. This is where I intended to start today, actually. This is the opcode, the 5 bytes, and the offset or immediate address, whatever it is, 32 bits. This I explain a very small point. It's not really, very small point, but it's a parenthetical point here. The offset immediate field contains a 16-bit sign number in the twos common method. Within the I format, there are actually 2 options. If the opcode field is different from 1, is not 1, then each value of the opcode specifies a different command of type 1, of type I. So, in other words, if it's not 1, then it's like I explained to you already. But if the opcode is 1, then there are several possible commands that this command could be, and the R2 field becomes the extension of the opcode. So the RT. In other words, this field, there are certain commands where the opcode will be 1, and I still won't know what the command is. I'll have to jump to the RT to know what the command is. And then actually, I only have 1 register left to actually use.
What's the purpose of that?
What's the purpose of that? For commands like, you think of a command that it would be. I'll tell you what the command would be. Branch if greater than 0. Branch, so I need the immediate field, if greater than 0. I know what I'm comparing to. I'm comparing to 0. So if what's greater than 0? If the RS is greater than 0, right? I only need 1 register. Branch greater than 0. And all I have to write is $T0 and some label.
Oh, cool.
Because if this is greater than 0, then go to this label. And that's it. I don't need another register. So what will we do to save? Again, we're trying to get extra commands and maintain that the opcode is still 6 bits. So I'm going to just put a 1 in the opcode, and then the RT field will actually serve as my opcode, essentially.
You could say it again, please.
I'm going to put a 1 in the opcode, and then the RT will tell me what actual command is. Because it could be branch greater than 0. It could be branch less than 0. There's several different commands that have only 1 register.
So the BGTZ requires an output of 1 and an RT.
And an RT to specify. I won't know what the command is until I look also at the opcode and also at the RT.
So at minimum, you need an OP and an RT.
So so we said there's 2 types. The regular one that I explained to you, the opcode will be some number here, and then these will be 2 registers, and that's the way I explained to you. But there's another one where the opcode is specifically 1. By the way, why can't it be 0? Because then it's an R type. So if it's 0, it's an R type. If it's a 1, it's this new special kind of I type.
Okay.
And if it's a 1, it's a new special I type where the actual opcode that tells me which specific command it is will be over here in the RT. And then I'll only have a label and an RS. And that'll be, like, for example, this command, branch greater than 0. I say this is parenthetical because it's like I could teach you that at any point. It's not, we're not going to continue using that, but you should know that. You should know that that possibility if the opcode is 1. But I'm not going to spend a lot of time on it. Here are examples of this B. I call it B type. There's the first one I call A type. I don't know if that's the official name, but I call it that, B type.
B type is when you use the RT.
B type is when you use the RT. So here are examples of them. Branch greater than 0, branch greater than or equal to 0, branch less than 0, branch less than or equal to 0. And then these one I skipped, but it's essentially the same thing. It's basically just that. Branch greater, branch less than 0. Branch greater than, this is greater than or equal to 0. Okay, let's go on. This is here, I want to show you something. notice this, we didn't talk about this column over here. This column is like this mathematical way of explaining. Look at add. Add is the easiest one. Look how you have to read this. Register, this is R, register RD. This equals is like mathematical equals, so it's like gets the result of the register value of RS plus the register value of RT. If we go to subtract, we'll see register RD equals the register of RS minus RT. So this is, if you forget, like which is it? Is it RT minus RS or RS minus RT? So you can look here and know which one is doing subtraction from which. This is like a technical way of understanding it. Now if you look at, let's look at a load word. Load word, RT gets the value of, what does this M stand for? Memory. Memory location as indicated by the RS register. Sorry, I'm looking at the wrong place. Load word here. The RS register sign extended. Plus the sign extended immediate. What is sign extension? You should have learned that in digital systems, but you didn't probably. Sign extend, but you should have. Sign extension just means like this. If I have the number, sign extension means like this. If I have the number, what number is that? 15, right? Positive 15.
Oh, the one, yeah, we did sign value.
Now, wait a second. What if I want to add it? What if I want to add it to, what's this number?
Are we in two's complement or not?
Two's complement.
Or are you two
And you-
somewhere?
Oh, gosh.
That's always a question.
Wait a second. 1, 2, 3, 4. 1, 2, 3. What's the result of this addition?
Well, you just first.
So the answer, this is, what number is this, first of all? You have to know this number.
On top of
Yeah,
my
everybody
head.
has to know this number. It's like,
Zero.
if you, no, it's not 0, 0, 0. Negative 1.
What?
It's negative 1.
It's in two.
In two's
Oh,
complement,
compliment, oh, okay.
in two's complement, this is negative 1. If you remember that, then you'll know all two's complement. Because everything else is derived from that.
Is that 1.101 or?
No, this is negative 1.
Because you changed
No,
everything.
but
Oh, that's
there's-
not.
Oh, okay, okay.
This is negative 1. So what's the answer of 15 plus negative 1? 14. But if I can't do this math because I don't have enough digits here. I have to have, in order to do math in a computer, you have to have the same number of digits between these two numbers. So what we do is we sign extend the number. Basically, all that means is I take the sign bit and I extend it over the course of the whole thing so that I can, what, you did learn that?
Yeah, like very like brief.
We just didn't call it
mentioned
sign
Yeah, we
extension,
didn't
but
call
we
it
just-
that.
What'd you call it?
You just said to add zeros.
Oh.
If
Or
it's
add
negative, add
Who was your
one.
teacher?
Dr. Lerner.
Who?
Dr. Lerner.
Who?
Dr.
Dr.
Lerner.
Lerner?
Shimon Lerner.
Shimon Lerner.
He was a good teacher.
He didn't use the, he's a good teacher?
Yeah, very
Yeah, okay, good, but he should have told you it's called sign extension.
Maybe he did.
He might have.
He might have. I'm glad you have a good teacher in that course because it's a basis for this course. So, okay, so anyway, that's what sign extension. If the number would have been, this number, then that's a negative number, right? It's some large negative number. So then I would put ones here. Yeah?
Yeah.
So you sign extend, you take the sign and you extend it. That's why it's called sign extend. So what this line says here is load word, take the register RS and sign extend the immediate value. Because with the immediate value is only 16 bits. But in order to add it to a register, which is 32 bits, I need to have a 32-bit immediate. So I'll just take the immediate and I'll sign extend it. So now it's 32 bits.
And
Okay.
with this sign extend, it knows what to do.
Yeah, how exactly? This is what the computer's job is. The
Where's the
computer's
transfer?
job is to do this
Okay.
and put the value in RT. Let's look at store word. Store word, look at this. Here, RT, you see, load word is very important here, guys. Very, very important. The the load word here is the RT is on the left side of the equal sign. Let's go to store word. Store word, the RS sign extended is on the left side, right? The RS plus the immediate is where I want to store the word. So that's on the left side. In other words, the RT is going to there, right? I'm taking the RT and I'm storing it in memory. What memory? Whatever location is stored, whatever location is indicated by the RS plus the offset of the immediate after it's been sign extended. That's how you have to read this.
From
What's
right
the
to left.
immediate?
Well, you always read it. You read it like you would in computer science. This is the the left side is always the destination, and the right side is the operation. But here, the left side, the destination is the computation of the immediate value plus the address stored in RS.
And the immediate value.
And that's where I'm going to store to, and where I'm going to take it from whatever in register RT.
And the immediate is the number that you get.
Is that 16-bit digit? It's a 16-bit number. Okay. So here I'm just explaining in that here is that same thing. The load command loads a word-sized datum from memory into a register. The format is load word, RT, offset, RS. The action performed in the load command is RT gets the value of the memory at RS plus the offset. Memory means the contents of memory.
Where's the sign extension? Oh, this is
You're right. I should have put the sign extension there.
the sign extension of the offset.
Yes,
Okay.
is the sign extension of the offset. Explanation. Well, that's what I write here. Offset must be sign extended to a 32-bit address. For positive sign numbers, zeros are placed in the upper 16 bits. For negative, ones are placed in the upper 16 bits. That's what I just explained. The offset now indicates the number of addresses to jump to. Then the processor adds the content of the RS to the newly extended offset. Now we have the absolute address. What do I mean by absolute? Absolute means from 0 to the end. In other words, a reference based on any place in memory, not a relative to a certain location, but the absolute address. The contents of this address are transferred to the RT register. That's what I meant, RT over here. So for example, load word 32.3 becomes T0 gets the value of the value of this plus 32.
Plus 32, like plus 32, like.
The memory location, take the 3, add to it 30, and add to the number 32.
Add to the number 32.
And then go to that memory location and take it and put it in.
Okay.
This is something
you're grabbing what's
I'm grabbing what's in the memory at location, whatever stored in register 3 plus 32.
So let's say register 3 was 3, let's say, and so you'd be taking what's stored.
Register 3 could not be 3.
Like 8.
Could be 0 or it could be 8.
So let's say it's
8
so
and
then
32
you're
would be
taking what's
40.
in 40.
Exactly.
And then you're storing it into T0.
Mm-hmm.
We don't write it like that. It's just what's happening.
What? Anyway,
We don't write it like that.
we don't write. This is just like writing. This is just explaining it. Yeah, this is good.
Oh.
Another example of I'm just sort of repeating what we already know. I'm really repeating what we already know because this was like meant to be the beginning of the next lecture, which you already knew. So now I'm repeating. Another example of I instructions is store command. This command stores a piece of data located in register RT into memory location indicated by RS. The calculation of the address is the same as the LT, as we have to do the sign extension. After calculating the address, the processor transfers the content of the RT register into the memory register calculated above. So, for example, if we would do store word 3 into 4 at plus 10, so it's memory 100 plus 4 gets the value that was in 3. This is really just explaining that green card. The third type of I instruction is the branch. So wait a second. We saw a load word, a store word, which we consider different types, and now a branch. a third type of I instruction is a branch. I mean, obviously we know a fourth type, which is the add I. But a third type of I instruction is a branch. Branch instructions compare the contents of two registers and perform conditional jumps. This is all review, right? BEQ, if they're equal, go to offset. BEQ directive means compare, and if there is equality, jump to a different line of code of execution. This jump may be forward or backward. It is relative to the current location. In other words, this is already a hint at the solution of how we're going to get a 32-bit address into a 16-bit location, because it's relative address. How much forward and how much back? In other words, if I write 4 in my branch, it doesn't mean go to address 00004. It means go 4 forward. Go 4 bytes forward. So 4 would be kind of silly. But 8, if I would write branch 8, then that would mean go 2 commands forward. If I would write branch minus 8, we go 2 commands backward. Branch minus 12 would be 3 commands backward. Yeah. So it's relative to wherever I am at the moment. You understand? It's not an absolute address. Understand the difference? Questions? Not understand the difference? A relative address means, like, if I would say to somebody, if I would, what's your name?
Adina.
Adina. If I would say, Adina, sit 1 seat over from Shulamit, that's relative to where Shulamit is. But if I would say, Adina, sit at GPS location 1100, something like that would be an absolute address. That address has no reference to anything else. It's just, we took the whole world, we gave it addresses, and now where should we say? So a relative address means relative to what? To wherever the PC is at the moment, wherever the PC is. So here, look what we say here. So this line, you should now think about. If RS equals RT, that's our question, right? We're doing PS RS RT offset. Then the PC, remember we talked about the PC, which is normally going up by 4. The PC should not be whatever PC plus, it should not be PC equals PC plus 4, but it should be PC equals PC plus the offset times 4. What do I mean by that? If the offset is 1, then I'll multiply it by 4 and I'll get 4. So 1 will mean 1 line forward. But really I have to multiply by 4 to get 4 bytes forward. Remember, because every command is a byte, is 4 bytes. So if I say offset is 7, then it'll be 7 times 4, 28. It'll be 7 lines forward or 28 bytes forward. Is that clear?
So you have to multiply by 4.
You multiply by 4. The offset is multiplied by 4 and then sign extended to a 32-bit number. Has to be sign extended. Yeah.
The offset is multiplied by 4, so why we add multiply by 4 if offset is already multiplied?
No. That's what this line means. This is the line in math, and this is the line in English. I'm just explaining. That's not twice. We don't multiply it by 4 twice.
So
No, the offset will be 1, 2, 3, 4. The offset will actually be how many lines forward I want. Like, for example, here, if I want to say, if this go to line 4014, I won't actually write 4014. What will I write? I'm on line, let's say I'm on line 8, and I want to go to this line. So it's 1 line forward, 2 lines forward, 3 lines forward. I'm just going to write go to 3.
Even though the next one would be.
Even though 3 doesn't really mean like 400,000 B and B, because there's no code. It has to be multiple. I'm going to take this 3. That's what I'm going to write as my code. The computer will take that 3 and multiply by 4 and get 12, and then go 12 bytes forward and get to this byte. You see what I'm saying?
If you said.
the offset.
So I, in my encoding, will write 3. The computer will change the 3 into 12, and then it'll know to go to the right line.
Is the if statement a MIPS statement or no? Isn't that the?
No, all of this is none of this is MIPS. All of this is like what you call in Hebrew, a mifrat technique, a technical description. A technical description of the command.
Okay.
It's just a description. I can describe it in words or I can describe it in this technical language. In other words, that's the way it sees on the green card. It just looks like that. If RS equals this, then PC equals PC.
Isn't the
Also
offset automatically 4?
no, the offset is whatever I wrote in the 16 bits.
But
But-
didn't we say before that the computer automatically has a PC that's 4 and it just
No, the PC is automatically incremented by 4, but the offset is whatever I wrote in the branch. Remember, it's a branch. If these are equal, then go to this line.
okay.
I'm going to write over that line the number 3.
Offset are the lines of code.
What?
Offset are the lines of code.
Offset is the 16-bit value in the format.
Right.
And the purpose of it, if it's a branch, is to tell me how many lines of code. Go for it. Yeah. So yeah. Now we're back to the jump again. I'm sort of repeating again. Just so don't get confused that you're saying, wait a second, did we already say this? Yes, we already said this. Unconditional jump. There are only 2 commands of this type, but I mean, I'm repeating it, but I'm adding a little bit more detail. There's a jump and there's a jump and link, which, what does the jump and link do? It adds, it's another command. It automatically increments, I'll just say it very quickly because you should do it in the lab, but it automatically adds the current location, the current line of code to the RA register. Why do we want to put the current line of code? Or I should say the next line of code. The current line of code, because the idea of the jump and link is to do a function. What does a function do? What is a function? You all use functions. What is a function? A function is jump to some other location, do a whole bunch of things, and then what?
Return.
What?
Return.
And then return to where? To wherever you were when you called me, to the next line. So how are we going to do that? How are we going to implement that? So what we're going to do is we're going to have this jump and link. It's automatically going to put in register RA the location where we have to return to. And that's why it's called register RA. Why? What does RA stand for? Can somebody guess? Return address.
Yeah.
You two of you together. That's why you're sitting next to each other. Return address. The address that I want to return to. So jump and link does 2 things. It jumps and it links. It jumps to a location and it puts where I have to return to into the RA register. How to actually use it, you'll do in the lab. Unlike BEQ, so here's unlike the BEQ, the target address we need to compute is an absolute address. So the BEQ, I said we write 3, and it's just going to say 3 forward, 3 back. -3 would be 3 backward. It's just how many lines of code to go. But so actually we already solved the problem kind of the square of the triangle peg into the round hole, because the branch didn't be saying like this. We don't need a 32-bit address. We're just going to take, it's a relative jump, and it's just so it's going to. I'm not going to be able to jump everywhere in memory, but I'm going to be able to jump within a range of 32 of 16 bits forward and 16 bits backward from wherever I am. From wherever I am in code. You understand that? I've got my code here. If I've got my branch, I can jump forward up to 16 bits forward and backwards up to 16 bits, right? No? I feel like I'm losing you guys. We've been here a long time. Wait, when are we finished?
12:30.
Oh, if we don't take a break. If we don't take a break, 12:30, right? All right, so drink some water, wake up. We got to keep on. We're now going into new territory. We got to do that.
Okay, we're in territory now.
We're kind of going to new territory, yeah. Yes. So it's an absolute address. We're actually going to deal with this question of how to fit the square peg into the round hole. We need to compute a full 32-bit address from these 26 bits. So now we're going to explain how we can do it. Okay, that was the question we left you with. How do we get 32 bits out of 26 bits? We don't have that, just repeating, we don't have that problem with the branch, because the branch is, we're going to get a 32-bit address because it's a relative address. We're going to take the current location of the PC, we're gonna add it to the 3 that we got. We're gonna multiply the 3 by 12, and then we're gonna add by 4, sorry, get 12. Then we're gonna add the 12 to the PC, and since the PC is a full address, we'll have a full address, right? If you take a full address and you add 12 to it, so now it's a full address plus 12, so you'll also have a full address. So with the branch, we've already solved the problem of getting a 32-bit address.
Because you're just jumping.
Because we're jumping, always we're gonna take the PC and add it to whatever index whatever offset we created. So we're always left with, again, a 32-bit number. The only limitation, what did we lose? We lost that we can't branch all, a million lines of code forward or a million lines backward. We can only branch 32,000 lines forward or 32,000 lines backward. That's pretty far, but we cannot branch more than 32,000 lines. But we'll eventually be able to get there because as the code progresses, we could do a series of jumps, right? As the code progresses, we could get there. Okay. Computing the jump address. So now we're back to the square peg. How do we get a 32-bit from a 26-bit? So since all code addresses are multiples of 4, right? All code addresses are multiples of 4. There's no line 400,002. There's no 400,004, 400,008, 400,012. We can safely add 2 zeros to the right of the address, thus reaching 28 addresses. So another 28, thus reaching a 28-bit. There should be a B there. 28-bit address.
Why can we? Because.
In other words, the jump is, we have 32 bits, right? 31, 0, the first 6 bits. 6 bits is the opcode, and 26 bits is the address. But why don't I do like this? If I want to go to address 1,000, I'm going to write 250. Well, I'll give you a simpler example. If I'm going to write, I want to go to address 4, okay? I'm not going to write 4. How would I write 4? 4 would be 0, 0, 1, right? If I want to go to address 4, I would have 0, 0, 1. No, I'm not going to write that.
Oh, just straight.
I'm going to write a 1 here. And then the computer will add 2 zeros to it. So I'll get 1, 0, 0, 4. Say, well, what if I want to go to Mamish address 1? Well, there is no address 1. I can't go to address 1 because it has to be multiples of 4. The first address is 0. The second address is 4. So either I'll write a 0 here. If it adds zeros to it, it's still 0. But if I write a 1 here, it'll be a 4. If I want to go to address line 8, what do I write? I'll write 2.
You write 1, 0.
I'll write 1, 0, which is 2. And then it'll add 2 zeros, and I'll get 8. So I actually, if I always add 2 zeros to whatever it writes, whatever I write there, then I'll be able to, then I've already got a 28, essentially I've got a 28-bit address, right? So I've worked myself up to a 28-bit address. I still don't have a 32-bit address, which I need, but I've got closer, right?
So why don't you just add more zeros?
Well, if I add more zeros, we're on the left. If I add more zeros on the right, then I'll never be able to get address. If I added like a whole bunch of zeros here, then I'd never be able to get to address 4, right? Because if I put a 1, the smallest number I could put here would be a 1. And if I added a whole lot of zeros every time, then I would never be able to get to 4. So I can't add more than 2 zeros. So how am I going to get, about everyone sees that I got a 28-bit address? So now I just need how many more bits? 4. 4 more bits and I got a 32-bit. So where am I going to find them? Remember, we're engineers. I got to just find some bits. So then we add the first MSB, most significant bits. I'm calling it that. Most significant bits. We add the first 4 bits of the PC, i.e. the address of the next command. Remember, we said the PC is always pointing to the next command, to the left of the address. This gives us an absolute address So in other words, what I'm gonna do is I'm gonna say like this. The PC has got some value in it, right? The PC is always pointing to the next line of command, right? It's got a value in it. So here's PC. PC is 32 bits. And it's wherever I am in code right now, right? Or it's the next line. Yeah, you're with me. This is something, this PC. It's some place in code. It's an address. I'm just going to grab the first 4 bits here. 1, 0, 1, 0. Who knows what they are? And I'm going to take this 28-bit address that I got here, and I'm going to append it. So I'm going to have the 4 bits of the PC plus the 26 bits from here called the offset, or maybe it's not offset, maybe it's 26-bit, whatever you call this address, and then plus 2 zeros.
Like the 2 zeros.
Well, that's what I said, these 2 zeros here.
Why does the
I thought we used
the bits?
No, the actual address, if I want to know what the actual address, what I'm going to write over here is 1. But I want to compute now what the actual address the computer will think I mean. What will it think I mean? It will think I mean this. 1 with the 2 zeros appended, then a whole lot of zeros, and then whatever the PC's first, so it will think I mean not address 4, but address some larger number. I don't know, whatever number that is.
So you're still limited to the scope of the PC.
So now what's going on is like this. Like, again, exactly. I've created, I've pieced together a 32-bit address, but I'm limiting myself now because I can't, if my PC is this, then I can never get to address 4, right?
Why not?
Because I'm stuck with these first 4 bits, which are like making my number much larger. But that's kind of okay because if you think about it, what is the PC? It's where I am in code. And what I'm at line 25 of my million line code. Chances are I want to jump to a reasonably close location to that wherever I am. You see what I mean?
Like you could
I'm-
jump around.
I could jump very far to wherever my PC, if I'm at line 10,000, then I can jump to line 20,000, 30,000 until as long as I'm within the range that these 4 digits indicate. Now, it could be a problem. It could be a problem because let's say I'm at, here, I'll show you, I'll show you, to explain this idea of range, I'll show you with a problem. The problem, and this is often a test question on the exam. The problem is, let's say my PC, let's say this is my PC, right? My PC is some number. For sure, there's 2 zeros at the end, right? Because it's got to be. So that's my PC. I didn't write 32 numbers here, but let's imagine I did. That's my 30. Now, I want to jump. Wait a second. No, I'm going to change it. Sorry, let me change it. It's like this. Okay, that's my PC. Imagine that's my PC. It's possible, right? That's a PC.
It's a big number.
It's a big number, but well, this didn't really change it. This is the significant bits, right?
But if you get any bigger, you're
Oh, exactly.
problem.
So now that's my PC. I want to jump, 2 lines forward. Can I do it?
No.
So you understand, I can't do it. Let me explain why I can't do it. You're right. I can't do it. I want to jump 2 lines forward. So what am I going to do? I'm going to,
Probably you're maxed out.
Wait, add 8.
what? Wait, what am I going to
You're
do?
essentially maxed out.
I'm maxed out because if I would jump 1 line forward, in other words, the address that I want to jump to is well, it's hard to write this number big, 2 more than this. What is 2 more than this? It would be like this, 1, 0, 1, 1, and then lots of zeros, right? And then
You would have a one.
and then 1, 0, 0, 0. That would be, right, I added 2. Well, if I add 1, then it would be 0. No, so 1. I take it back, 1. That would be 2 lines forward, right? If I add 1 to this, then these would all turn to zeros, right?
Yeah.
If I add 1 to this, these would all go to 0,
then
and this would become a 1. I want to go 2 forward, then this all goes to 0 except for this one becomes 1, and this also goes to 1. This stays at 1. So this would be 2. This is the address I want to go to. If that's the address I want to go to, what do I got to do? I got to take this section of it and put it in my offset and put it in my space, right? That's the 26 bits. These are the 26 bits that go in my jump command. Here's my jump by 6 bits. And the 26 bits will be these bits, will be all these zeros, and then a 1 here. And then I'll take that number, I'll add 2 zeros to it, Yofi. And so far it's good. And then I'll leave all the zeros. But then I'm going to take the PC. The PC is still this. So I'm going to do 1, 0, 1, 0. And I'm going to go to a completely different location. I'm going to go backwards. I wanted to go 2 lines forward. I'm going to go thousands of lines, millions of lines backwards. I'm limited. Yeah.
So is there an option to add one more line and change the PC? Can I jump PCs?
Can you jump PC?
I think
Yes.
I'm preempting that this will be a problem. I know this will be a problem, so I'm gonna preemptly jump the PC to the next.
Yes, you could.
Okay.
You could definitely. You don't even have to jump the PC. You know what you could do? If this was the exact case that you had, then you could write as a special command, which Avi likes to talk about sometimes, which is called the NOP, no operation, like a blank line. So I could do like, let's say I'm doing whatever my command is, blah, blah, blah. And then I do NOP, and then I do my jump. And then I do my jump, whatever, wherever I want. So the NOP is a no operation. It's an operation that does nothing except for one thing it does
It
do.
jumps you.
It increments the PC by 1 line because it's a new line.
Oh, cool. So if you know.
So
that
if I know,
that's smart.
it adds me forward to the PC. So if I know that I'm exactly at the border, then I can push myself over the border, and then I've up the thing, and then I can jump. Yeah, I could do that. But I mean, it's hard for me to imagine a scenario where you would know where you are. In other words, when you write code, you don't keep track of where
So much of the program.
what line you're on. But if you think about it, if I'm writing in C++ and the compiler is putting it to machine language, and I did some jump to some faraway place, the compiler has to keep track of the lines. The compiler has to be smart enough to let me do it. You see what I mean? The compiler is going to have to add these NOPs. Think of how complicated the compiler is going to be to write. I, as a C++ program, don't know what line numbers I'm at, but I decide that I want to jump to a function that's 1 billion lines forward, So the compiler have to deal with it. You have to solve that problem for me. I don't think in your compiler course, though, you're going to talk about that. Because the compiler course is maybe you will. Maybe you'll talk about how to solve these jump problems, or how to identify them. The solving is not the problem. The problem is to identify them. How do you identify it? But anyway, everyone understands how I created a 32-bit address from a 26-bit address. I added the zeros. I added the 4 digits from the PC. I have a limitation now, but I do have an address that I mostly will be. I do have an address that's 32 bits, and most of the time that limitation won't be a problem. Here's a summary of what I just said. The address is going to equal, see, this is like, again, a technical description of what I just said. The address will equal bits numbers 31 through 28, which is the 4 leftmost bits of the PC, plus the target address, which is in that space, that 26-bit space, plus 2 more zeros. Cut and paste it. Now let's do an example where we do an encoding of a jump. We're a little bit behind, actually. We should be, have to go faster. I'm telling you too many stories. So here's an example. This is like an exam question, okay? Suppose we want to encode the command jump 10,000, i.e., we want to jump to the real address 10,000. Assume the PC is 4. Shulamit, tell your neighbor to put her phone down. What's your neighbor's friend? Put your phone away. What's your name?
Gabriella.
Gabriella. Oh. Were you, there were two
I took your
Gabriellas
class for like a week.
last semester, last year? The last semester, yeah.
But there are two
What's your last name?
Gabriellas. Green.
Green. Yeah, right. I remember there were two Gabriellas and then there was one.
Yeah.
So you're the other one. Okay. Glad you stayed in school. Okay, so suppose we want to encode the jump 10,000. We want to jump to, now assume the PC is 4. What address do we need to write as the target? In other words, what address do we need to, that's what we want to do in reality. But how is it going to be encoded in the language, in machine language?
What do we mean assume the PC is 4? Doesn't it always increment by 4 anyway?
Yeah, but this is a on paper example. Assume the PC is the value 4.
Oh, it's the value.
Meaning the first 4 digits is
okay.
0, 0, 1.
It's all zeros
0, 0.
except for the last, except for 1, 0, 0.
Okay.
What address do we need to write in the target? So here's the answer. Since the processor will multiply whatever target index we give it by 4, we should write 2,500. Because 2,500 times 4 is 10,000 to get the desired 10,000. And we can ignore the PC since its 4 bits of the most significant bits are 0. As the 4 leftmost bits are 0, if it's a 4, then those will be zeros. So the opcode for J, now we have to say, wait a second. The opcode for jump is 2.
Because there's 2 zeros.
In 2, but notice there's a certain problem here,
Why is it
which is, that's the opcode. Because I go over here and I
That's
look,
what it says.
jump, and it says 2.
Oh, okay.
The opcode is 2 for jump. I don't know anything, we use this paper. So the opcode for jump is 2, but notice there's something funny about the opcode. And it's always true of all the opcodes, there's 6 digits. But 6 digits is kind of weird because 4 digits is a hexadecimal digit. So if I want to write this in hexadecimal, I'm going to write a 0, and then what's this going to be? This is going to be 1, 0, and then whatever the rest of the target address is. But the target address is all zeros because it's 2,500, but 2,500 is very small, so the left side of it will be all zeros, right? So I can already see that it's going to be 1, 0, 0, 0. What's 1, 0, 0, 0?
1, 0, 0, 0, 8.
8. So it's going to be 0. So look what I got. So the encoding should be 0, 8. See how I got the 8?
I'm still confused why there's a problem with the opcode.
There's no problem. There's no problem. I'm just saying, how do you write it in hex? If I write in all 1s and 0s, then Gage is to, hey, go write 1. I'll go write 32 digits. I want to write in hex. So how do I convert this number into
So you have
hex?
to take each
I have to take each
digit.
each
Oh.
set of 4 to
Okay.
convert. And this set of 4 is sort of the next set of 4, part of the 4 is in the opcode and part of the 4 is in the remaining bits. So
Okay.
and I happen to be able to guess that they're zeros because I can guess that the conversion of 2,500 is going to be a lot of zeros and then some 1s and stuff. So I'll
start from the right side though.
yeah, you can start from the right side.
So then if you,
So then you'll get there and you'll get it right. Yeah. I'm starting from the left side.
What's the 0,
right,
0,
but
9
that changes the number.
No, it'll be the same because they're equal amount though. It would only change the number if there was like 30 bits. But because it's 32, it's an even number.
Oh, it does say the same.
Not even in the sense of even as.
Anyway,
odd,
this is the
even
0.
in the sense of fours.
Look, now what is this number? If you somebody put this into their calculator and convert it to decimal.
In decimal?
Convert that to decimal. 9C4.
C is 12, so 12 times 16 plus 9 times 256.
Yes, I'm on it.
And that
No,
number
you have a-
is?
No, you can go to a website and just type in hexadecimal decimal
Oh.
converter.
No, but I'm on decimals.
We're gonna do it.
A, B, 10.
Oh, you-
C is, I'm overachieving.
You're right. You can do 256 times 9. 256 times 9.
2,500.
It's 2,500.
Hey!
It's 2,500.
We could have done that without doing the calculator.
Yeah,
Wait, so
Well,
what are the
just
three
checking
zeros?
that I'm right. This is 2,500. When I multiply and I add 2 zeros to it, I'll get the computer. Notice, this is what I got to feed the computer. This is the series of ones and zeros that I need to give the computer to get the result that I want, which is jump to location 10,000, right? To jump to location 10,000. I got to give it the 0 and then the first 2 digits of this 8 tells me to jump. And then the rest of it tells me how much to jump. And then it's going to multiply by 4.
Wait, which one tells you to jump? The 0 and the 8?
The 0, not the 8. It's not always 8,
Oh.
right? It could be, if I wanted to jump to a location that was like not 10,000, but like some millions or billions, then I might end up with in other words, really what's going on here is I have like this. I have the 0, 0, 0, 0, 1, 0. That's the opcode for jump. And then I have, if the place I wanted to go to was some large number, like 1, 1, 1, 1, 1, 1, 1. Yeah. That's where, and then what happened is when I would start writing it in hex, I would look at this and I would say 0. And I would look at this and I would say 8 plus 3 is 11. No, B. Right? So it would not be 8, it would be 0B.
Okay,
So the encoding, so if I write it in hex, I have to know what the next 2 digits. I can't just look at the opcode and say it's 08. It's not always 08. It's 08, assuming that there's no 1s over here, assuming that there's 0s over there.
So what does the 8 represent though? Like what would we call, like the 0 tells you that it's a jump. And then
No. The 0, 0, 0, 0, 1, 0 tells me it's a jump. The opcode is 6. It's a little bit of an annoyance that opcodes are 6 and not, it would be wonderful if opcodes were, let's say, 8 bits and then registers were 8 bits and every register was 8 bits. I'd have a lot of wasted space. Registers are 5 bits. That's really annoying. 5 bits, it means that when I translate it into hex, it's going to be cutting on weird locations. It's not going to be cutting at 8s.
So you'll have to have 3 bits.
Well, we'll see what the encode, you have to try for, I should give you as a homework assignment, but I think there are some work assignments, but try yourself to encode an add command. An add command has, see what I'm saying by encode? Take an add command like add T0 T, to add T0 T1 T2, and then write it out in hex. In other words, I did for you in the previous slides, I did for you with 1s and 0s. I never translated it into hex. The translation to hex, once you have the 1s and 0s, is no problem.
Right.
But the problem is going from decimal to hex is a little bit of a problem. It's a little bit.
Can you do from decimal to binary to hex?
Yeah, you can do from decimal to binary to hex. Then, yes, you can do. That's in fact what you have to do.
Are there?
You have to do decimal, binary, hex. If the answer, like on the exam, the answers might be multiple choice and they might be in hex. So you're gonna have to do decimal, binary, and then hex. You can't really go directly from decimal to hex. But let's do another example, and then this may be even more clear. Or the other example is something kind of what we did already. Suppose the PC is not 4, but is FA0004. How would we encode that same command? So theoretically, the command would be the same as above. It would be 08, etc., 9C4. Because the opcode and where I want to jump to. But since the processor is going to append 11111 from the PC to the address we give it, because why will it be 11111? Because F is 4 1s. Well, and that's it. That's the 4 1s. So we will not be able to jump to this location. It is too low of a location. In other words, the answer is, what's the encoding of jump 1000? The answer is impossible. It's an impossible request. If I'm at, and just think about it, I'm at line number some 10 billions or something. I'm at line number, not 10 billion. I'm at line number 1 billion, some huge number, F8, FA, that's the PC. That's the line number I'm at. And I want to jump down all the way to the bottom to line The very, very beginning, 10,000. It's too low of a number to request. You can't jump that far.
Why?
Because I'm stuck with this F over here. That F is gonna be appended to my address no matter what I do. And that's going to, it's like if my boss tells me, I'm gonna give you a 6-digit paycheck, and the first 2 digits are gonna be 1, 2. How much money would you like? And the person says, I'd like $4. It's impossible. I can't give him $4. If the first 2 digits of my 6-digit paycheck are 1, 2, then I've got to give him at least $120,000. Right? I can't give him $4 because I told him the first 2 digits, I'm telling you now, are 1, 2. Well, that's what I said here. The first 2 digits are whatever the PC's the first 4 digits are whatever the PC's first 4 digits are, and they're F, so that's 4 ones. So you can't go to this tiny location. All right, good. We'll stop here. This is actually the end of chapter 2. This 3 means the beginning of chapter 3. So if I ask you next time where we got to, we're at the beginning of chapter 3.
Are there curriculum in this class?
What?
Are there curriculum in this class?
There are. We're just getting them translated and,
Oh,
So we
okay,
don't
because
have
the first one said it's given 5 days.
yeah, forget about that.
So we don't have
Oh, actually, no, I'll put it up now and I can give you, I'll put it up today. I think I got it. She told me that they came in. So look for homework assignment. I'll give you more than 5 days, but not much. I'll give you a week. Usually the first assignment is a review of digital systems. So if you hated that course, you'll hate this.
Thank you.
Glad to hear it.